water flows through a pipe at a rate of 3 kilograms per second. So I'm going to triple highlight this guy here, because you guys have been dealing with air for such a long time that now water shows up and you completely disregard the fact that it's water and not air. And a lot of you guys jump to the wrong tables. Flows through a pipe at 3 kilograms per second. It enters at 5 Celsius and exits at 15 Celsius. Okay, so before I even continue, right, if we know the mass flow rate of water, the temperature it enters and the temperature it exits, we know exactly how much how much energy it absorbed, right? We know exactly. That's very easy for us to calculate. But moving on, through a 5 centimeter inner diameter tube. So this is inner diameter here. The tube was constant at 90 Celsius, and assuming a fully developed flow, so that was straightforward. What is the length of the tube? So how long this tube has to be so that with a 90 degrees Celsius wall, we can increase the temperature of the water from 5 to 15. So once again, I'm going to cheekily use the same image we had before. I'm going to adapt this image to what we have now. So we don't have air anymore, it goes away. This is not 500 anymore. I don't know this yet. I do know T1 and T2. The diameter is not the same. The length I don't know, I'm trying to figure out. This is not air. Pressure is not this. And the mass flow rate is not this. Okay, so what do we know? T1 is 90 Celsius. T1 is 5 Celsius. T2 is 15. This is water, not air. So let's put water over here. And actually, let's draw this, make it as lively as possible for anyone who lost their connection and jumps in. So I don't think I can highlight its water any more than I did. What else? We know this is 3 kilograms per second. And I think that's pretty much it. And we know this is fully developed. Okay, so the diameter, 5. Okay, we need to find what is the length that would allow this situation to happen. Okay, so hopefully you guys already figured out what we need to do, but the idea is very similar to the first problem, right? Because note that we know that Q is flowing from the wall into our fluid, right? We know Q is flowing from the wall into our fluid from both sides, right? Just to remind you, or for all the sides, I should say. And we also know how much energy water requires. We know how much 3 kilograms of water needs to go from 5 to 15 Celsius, right? And if it's a rate of water, that is, if the water keeps coming, then we need to keep giving energy. So we also want a rate of energy. So we can find how much energy this water needs to go from 5 to 15, and then we can use Newton's law of cooling to say, okay, if I need this much energy, then I'll require this much area. And if I use this much area, then that will be related to L, and we can find L. So that is our game plan. To find Q, with Q we can find A. With A we can find the L. There's just one slight problem, which is your old friend convective coefficient, right? Because we're going to have to use that eventually when you use Newton's law of cooling. So we might as well start by finding H, because we're going to have to. It's going to be the toughest thing in the problem. I'm looking at table A9 this time. So this is on your book. It's also on the sheet that I gave you guys. And if I'm not mistaken, it's also on the lecture slides from the convener. So let's go ahead and plug these guys in. Boom. Okay. You'll see the table has the 10 Celsius already. You'll note that I'm using 10 Celsius because we don't have the bulk temperature now, right? We have 5 and 15, so we know the average temperature through which this pipe will be. Let's rephrase that. We know the average temperature, the average difference in temperature between the wall and the fluid, which is a thing that is driving the convection, is going to be from 90 to 10, so 80 degrees Celsius on average, right? So that's why I'm grabbing the properties of water at 10, because we know that the properties at 5 will be one, at 15 will be another. So we take the average at 10 and we get those properties. Okay, again, table A9, not to be confused with A5 for air. Okay, I want to find Reynolds. If I want to find Reynolds, then I need to once again multiply density by volume by diameter, right? Divided by my dynamic viscosity. Once again, I don't have the velocity, so I can do the same thing as before, because my velocity times my cross-sectional area has to be equal to my mass flow rate divided by my density, which means that the velocity can be also found as mass flow rate divided by density cross-sectional area. And this is the same thing as 4 times, 4 comes from the r over 2, diameter over 2 squared, density pi diameter squared. Okay, so I can plug that into Reynolds. Once again, I'm doing the whole thing so that we're all on top of what's happening. And then my velocity will become 4 mass flow divided by density pi diameter squared. Diameter and diameter squared, density, density. So this will just be mass flow rate, which is, I forget, 3? What is it? 3, yeah, 3. 3 kilograms per second times 4 is a constant, divided by viscosity, 1.31 times 10 to the minus 3. It's very small, isn't it? Pi, diameter, which was 25, was it? Oh, 5 centimeters. Let's just check units, because we've been doing this for a while, and we haven't checked the units on this one before, so let's just go ahead and check units just to make sure we're doing the right thing. We have a mass flow rate that will be kilograms per second. Then we have our viscosity. Dynamic viscosity is kilograms meters per second. We also have our diameter, which is measured in meters. So hopefully these all cancel out, and we have a Reynolds without any units. Kilograms, meters, seconds. Cool, we're doing the right thing. Okay, so that means my Reynolds is 5.8/316. Which is turbulent or laminar. You see that if you look at the equation sheets, you see that when flow is laminar under these cases, generally the solution is very simple. So that's why you tend not to see these kind of questions, at least unless you do several questions, then you see that it might be a constant, it might be a very simple equation. So, okay, moving on. Just go ahead and do something quickly here. Okay, moving on. So turbulent, and it's been said that's fully developed flow, right? In the beginning of the problem statement, it says fully developed flow. So we have a turbulent plus fully developed flow. The equation we'll be using is exactly the same as the one we did on the previous one. So 0.020, where is it? 0.023, Reynolds 0.8. Parallel to the 1/3. No, sorry, parallel to the n. Let's make sure we're doing it nice, because fully developed plus turbulent. Is my fluid being heated, or is it heating up, or is it cooling down? We are going from 5 to 15. So this guy is heating up, so therefore n equals 0.4, right? N equals 0.4. So let's plug in the numbers. Sorry, not 0, it's 9.4. Nusso is 366. If my Nusso equals my convective coefficient times my diameter divided by my conductivity, then my conductivity equals 4,283.5. Okay, so we kill the beast, kill the troublesome part. All right, so now that we have that, we can go ahead and go and try to solve up. So how much energy the fella takes up, right? So how much energy is needed to take water from 5 to 15 Celsius? That's what we're looking for. Yeah, so let me go see if I want to copy this maybe. Let's go ahead and copy this. Yeah, what I want to answer now is how much energy is needed so that I can take my water from 5 to 15. Let's plug this in here. And we know how to answer that. We've known from the start we didn't need to do anything beforehand. We just need to do, if we want to know the energy, then it's going to be mass. The energy is going to be the mass times the heating capacity times the difference in temperature. If I want, however, to get the to put mass flow rate there, then I'm going to have a energy rate, right? So I'm taking derivative on everything, and we know these guys will be constant for this problem, so these stay. We can just do this. So how much energy that is? Well, that's going to be my mass flow rate, which is the mass flow rate. Yeah, 3 CP 4.195 and delta T 15 minus 5. Unit wise, kilograms per second, kilojoules per kilograms per Kelvin. I'm left with kilojoules per second, so I'm finding kilowatts here, right? So we're getting kilowatts. We get 125.85 kilowatts. And the question, if you guys recall, is what is L, right? What is the length that this pipe requires so that we can have all this energy being exchanged under the conditions that we're given? So we know Newton's law of cooling tells us that energy being exchanged will be this delta T. And in this case, remember that this delta T here is for convection, not the same 15 to 5, right? So we can break down the area, right? Because we know the area is the area through which convection is taking place. In this case, it's the area of the inside of the pipe. We have the inner diameter, so I'll go there. So that's going to be pi times diameter, or 2 radius times the length in our delta T. Okay, so note that we have this Q, we just calculated it. Oops. We have this Q, we just grabbed it. We have this H, we grabbed it before. We have this delta T, that will be our 90 minus our 10. We have the diameter, we have pi, obviously. The only thing we don't have here is the length. So let's find this. Let's find this fella. Q divided by H pi diameter delta T. This is 125.85 times 10 to the third. So I'm changing it from kilo. What am I doing? Yeah, I'm changing it from kilowatts to watts because I know that the H is in watts, right? H is in watts. Divided by H, we found it to be 4,283.5. I don't like doing this one. Let's do this one. Pi is pi. My diameter is 5 centimeters, so 10 minus 2 meters. And my delta T is 90 minus 10. unit-wise, I have h, which is this. Then I have pi that has no units. Then I have meters for the diameter, and I have Kelvin or Celsius for the difference in temperature. Watts and watts, meters, Kelvin, Kelvin. I'm left with meters, which is good. So we're looking for a length. Length is 2.34 meters. And there you have it. Okay, so now we have the length. Something interesting before we finish up this question is, if you guys go and do the analysis bit by bit, if you go ahead and do the same analysis that we did by relating the two equations and doing the derivative and integrating the whole thing, that is a more precise way, you get a different value. So this just goes to say that you are dealing with an approximation, right? Again, these are empirical equations that we're using, all that. So it's interesting if you're into this subject, if you're liking what you're learning, it's interesting for you to do that analysis, solve it, doing the differential analysis, and see how different your result is from this approximation. Okay, you don't have to.